Okay, so today we're going to learn how to come up with solubility using a KSP and maybe figure out a KSP from solubility data. Okay. Basically, what you're trying to do is trying to figure out how much of a solid is going to actually dissolve. We learned about soluble stuff earlier in the year, and soluble stuff isn't always soluble or it isn't soluble forever. There's a limit to the solubility, how things can dissolve, how much a substance can dissolve, right? So there are some things that are called insoluble, and for the most part, they're insoluble. They don't dissolve to a great extent, but they do dissolve a little bit. And there's an equilibrium between the solid state and the dissolved state. And they do make enough of a difference that over time they can create a lot of solids if they're dissolved in water, and these solids end up the concentrations of being building up, and they can deposit or precipitate out solids. So what we're going to have to do first is I'm going to go ahead. First off, I want to just kind of apologize or give you a heads up to apologize for the loud banging on the Chromebook that I'm using to write this on. But the stylus, I guess the sound is pretty sensitive to the stylus. So every time you hear me hit the screen with my stylus, it makes a big noise. All right, so first thing I'm going to do is I'm going to go right out. Okay, let me go ahead and let me get rid of that. I think I want to start off with just a pen. All right, there you go. We're going to write out, let's say, AgCl. Okay, so this is a solid, AgCl, which is considered insoluble for the most part. But it does dissolve to a small extent. And we're going to try to figure out how much how much it does dissolve with its KSP. KSP is an equilibrium constant for this reaction where it's going to dissolve. It's basically an equilibrium constant. That's why it's a K for the equilibrium constant. SP stands for what we call solubility product, and you'll see why in a little bit. Step one, though, before you can even try to solve the problems, you got to know what the chemical equation is here. And basically, I think we've done this before. It's just dissolving an ionic substance into its ions. So AgCl right here is basically, if you cut it right here, two elements, silver on the left-hand side and chloride on the right-hand side. All right, so we're just going to break it down into those two elements. And actually, we're going to break them down not just to the elements, but to their ions. So let me get rid of this here. I think I'll leave that there. All right, so what you're going to do is going to take your solid, and then you're going to go ahead and write the double-headed arrow to show that there's an equilibrium between the solid and its ions. And just write out the ions. So Ag is a +1 ion, and that's going to be aqueous. And chloride is going to be a -1 ion. That's going to be aqueous. We should already know from first semester what these ions are. But in case you need a real quick reminder, chloride right here is in column 17, and all the chlorine ions are chloride ions, and they get a -1 charge. Everything in column 17 gets a -1 charge. If you don't know that silver is a +1 because silver is a transition metal, you can take a clue from the chloride. Right, so here, chloride is a -1 right there. So in order for this whole thing to be neutral, there's one chloride, one silver. The silver here has to be a +1 ion in order for the silver ion and the chloride ion to kind of cancel each other out and form a neutral solid. Right? So that should all be reviewed. And actually, we did a worksheet that did similar things to this. Hopefully this is not too much a review. I know it's been a little bit, but that's what we have to kind of do here. Okay. All right, so right now we're just going to go ahead and practice on doing these, just breaking them up. Okay, so the next one, calcium carbonate. Now this is not all you're going to do, but this is a very important part of doing these problems. So you got the solid calcium carbonate, right? It's going to break up into two ions, and this is where, in these cases, basically your first ion is a metal, right? So you can break it up right here. And your two ions here are going to be calcium, and hopefully you can identify the carbonate ion, right? So calcium is a +2 ion from column 2, and carbonate is CO3, and it is a -2 ion, and they're both aqueous. Okay, same thing here, aqueous. Okay, and that's all. That's how we do it. Okay, now you've got to be careful because some of these do get a little tricky. Let me move this up over here a little bit. They do get a little tricky in the sense that um, some of them don't break up into exactly two things, right? The first one that we had here was, um, you know, silver chloride, just two elements, silver ion and chloride ion. Calcium carbonate had a polyatomic ion, so it's calcium ion here, and carbonate ion. Oops, how'd that go? Okay. But they still just broke up into two ions that canceled each other out. Sometimes we get two of one of the other, or three of one of the other, or three of one, two of the other. And so let's go ahead and see what we do when that happens. Once again, we've done this before, so I'm just reminding you how to do this. Lead chloride. If you're trying to figure out a problem with lead chloride in it, PbCl2. All right, so we've got a lead ion, and I won't put the charge on the lead ion because there's more than one charge to lead, so we got to figure out what the charge is on that. So there's going to be a lead, and there's going to be a chloride ion, not Cl2, just Cl, right? And each chlorine is a -1, just like the other one, right? So there's actually going to be two chlorides, okay? So in order for the two chlorides, which have a total of two negative charges, to cancel out with the positive ion has to have, there's only one lead, and it's got to be a +2. Okay, and they're both aqueous. And this is going to come into play in our, this aqueous thing here is going to come into play in our problems here. Okay, so really we're breaking this up right here between the lead and the chloride. And on all these is basically the metal separates out from the rest. If, you know, if there's only two elements, it breaks up into two monoatomic ions. If there's three more elements, one of your ions is going to be a polyatomic. The only polyatomic cation that we have is ammonium, and ammoniums are all really pretty soluble, so they wouldn't be in any of these problems. Okay. So just so you know. Pretty easy rule. The first element is a metal. You separate it from the rest, and you get your ions there. Okay. Let's do a third one, aluminum hydroxide. And aluminum hydroxide looks like this. The parentheses is kind of a giveaway. It tells us that, hey, you know what? We can go ahead and we're going to have to break the hydroxide up from the aluminum. But, you know, we already knew that kind of, even if we didn't have the parentheses to help us, because the first element is aluminum. And we're going to go ahead and break it up into aluminum. Aluminum gets a +3 charge because it's in column 13. And then the hydroxide is a polyatomic ion. It's got -1 charge. And because of the three out front, outside the parentheses, we put it out front. Right? So there's your aluminum hydroxide breaks up into aluminum ions and hydroxide ions. Okay, and that's how you do those. So that's part one of the solving for this, is to know how to write the equation. Because once you know how to write the equation, then you can go ahead and use that to do the rest of your problem. Okay. All right, let's go on to part two now. Now that you have an equation, once you've broken up an equation, now you can go ahead and try to find out solubility if you have a KSP. So let me go ahead and move these up here. All right, so let's say you're trying to figure out what the solubility is of, let's do that here. Solubility of AgBr. Okay, AgBr solubility. And you're given that KSP of AgBr is 5.53 times 10 to the minus 13th. Okay, that's enough for us to figure this out. All right, but the first thing we got to do is, as I said, write out the equation. So let's go ahead and write out the equation, AgBr. So AgBr is a solid. All these are solids. That's why we're looking at the solubility. So what is the solubility of AgBr? Well, Let's go ahead and write the equation. AgBr breaks up into silver ions and bromide ions. And both the silver ions, all ions are aqueous. They cannot exist as solids on their own. So they're aqueous. They're dissolved in water. And um, that's how they can kind of deal with being by themselves, as opposed to in a crystal lattice. All right. So now that you have the equation, let me move this up just a little bit here. Now that you have the equation, we can go ahead and write down what's called an ice table. And ice tables are used for all of these equilibrium problems. So these are basically easy equilibrium problems. That's why I'm showing them to you and having you kind of figure this out. So what we're going to do is I stands for initial. I'm going to put this over here on the right. So I stands for initial. These are the initial amounts or concentrations. C stands for change. It's a change until you get to equilibrium. And then E stands for equilibrium. And essentially what you do is initial plus change equals equilibrium. So we don't know how much of the AgBr is going to dissolve. So we're going to put this as X. And that's what we're looking for. And then we're going to assume that you're putting it in some water, pure water, so there's no silver ion and there's no bromide ion to begin with. Okay. And what we're going to do is we're going to try to figure out how much AgBr will be able to dissolve. So our X, it's going to be all dissolved. So all of it's going to dissolve. So for the change in the change row, we're going to say that whatever X we start off with, all of it dissolves. So we end up with 0 at equilibrium. And if X moles per liter of AgBr dissolve, then we're going to get plus X, the Ag ion, and plus X, the bromide ion. Because X moles per liter of AgBr turn into X moles per liter of Ag, and X moles per liter of Br minus. And so once you do that, now at equilibrium, X minus X, there's nothing left. And that's why we did that, because we want to know how much we can dissolve so that there'll be nothing left, and yet all of it will have dissolved. At equilibrium, the silver here will have X molar, and bromide will also be X molar. Okay, so we've got the ice table set up, right? And this is basically how you do all these problems. There are harder problems that are not solubility product constant problems that you set up similarly, but there's all these other things that come into it. But I'll show you how these kind of tend to break down and be simple. Really, the setup is all the same for all equilibrium problems, but the solubility product, the math kind of breaks down and becomes simplified compared to these other problems. All right, so now that we have that, we can write our equilibrium constant for this. If we're to write an equilibrium constant, we'd basically say K is equal to, and by the way, this K is KSP. That's what KSP is. It's an equilibrium constant. The concentration of the products, so that's silver ion and bromide ion, divided by the concentration of the reactants. So first I want to put the concentration of the products, Ag plus and Br minus. Right. Neither of them has coefficients, so therefore I'm not going to put any exponents. Okay. Let's see, what else? Oh, yeah, and divided by the concentration of the reactants, except that the reactant only has a solid here. And in an equilibrium constant, you only use aqueous substances and gases, not solids and liquids. So we don't need to include the AgBr because it's a solid, right? So basically, no solids in your equilibrium constant and no liquids, just gases and aqueous substances. And that's what makes it easy. All right, so now that we have that, we can go ahead and plug these in. So this right here is the concentration of silver ion at equilibrium. This is the concentration of bromide at equilibrium. So we're going to go ahead and plug them in here. This is going to go here. This is going to go here. And we're going to end up with X here and X here. It's going to give us X squared. Okay, so X times X x times x is going to give us x squared, and that's going to equal to the KSP. And we were told up here, if I go back, that the KSP is, sorry, this thing's not responding here. KSP is right here, 5.53 times 10 minus 13th. So we're going to plug that into here. Okay, so let me go ahead and move that down. 5.53 times 10 minus 13th is what said. 5.53 times 10 to the minus 13th. Okay. And now there's my equation. X squared is equal to 5.53 times 10 minus 13th. If you have x squared as your variable, how do you solve? Well, you take the square root of x squared to get x by itself. And since you took the square root of the left side, you took the square root of the right side. So you end up with that x is equal to, and let's go ahead and do that. 5.53 times 10 minus 13th, right? So we're looking at square root of 5.53. How did I do that? 5.53 times 10 to the, what was that? 10 minus 13th. Okay. 5.53 times 10 to the negative, 13th. Oops. Negative, there you go. Square root of 5.53 times 10 minus 13th equals to 7.44 times 10 to the minus 7th. If you can see that there. 7.44 times 10 to the minus 7th. And so, let me go ahead and use that. 7.44 times 10 to the minus 7th. Okay. And then that's a molar. Moles per liter, which means that that is my equilibrium constant here. I mean, that's the solubility right there. That's not an equilibrium constant. It's an x. It's my solubility right there. So that's what x ends up being. And so now this is my answer right here. Okay. That's the solubility. I can dissolve up to 7.44 times 10 to the negative 7 moles in 1 liter per liter of water for silver bromide. Okay. So that's how you would do these problems. Okay. So that's problem 1. Setting up the ice table, doing the problems. That's pretty standard. Okay. Let's do another one because there's some that like have little funky things going on with the math, but luckily with these it's not too funky. Let's go ahead and check it out. All right. Number 2, problem 2. Let's go ahead and figure out the solubility of, we're going to get solubility, whoops, let me go back to pen. Solubility of calcium hydroxide. Given that the KSP for calcium hydroxide is 5.02 times 10 to the negative 6. Okay. So we're going to do it the same way we did it last time. We're going to write out the equation. Calcium hydroxide is a solid. So we're going to go ahead and write out calcium hydroxide, solid. And then that's going to break up into, it's 2 ions, the calcium ion and the hydroxide ions. Calcium ions and the 2 hydroxide ions. Right. That 2 on the outside comes up to the front. Okay. So we're going to make an ice table like we did before. We're going to say there's X moles per liter of calcium hydroxide and no calcium ion, no hydroxide. So the initial line is basically, put it in water. There's no calcium ion, no hydroxide ion to begin with. All the calcium hydroxide is going to react. It's all going to be gone. And for every X moles per liter of calcium hydroxide you get X moles per liter of calcium. And you get 2 X moles per liter of hydroxide, right? Because of that 2, right? Because of the 2 here, we get twice as much. So 2x for that. So at equilibrium, there will be no more calcium hydroxide. There will be X moles per liter of calcium ion. There'll be 2 X moles per liter of hydroxide. Okay. And here's my KSP, 5.02 times 10 to the minus 6. All right, so now that we've got our table, we can go ahead and do the calculations. Right. So this is a good place for questions if anyone's got questions as to how we set up the table or we got anything. All right. Now that we've done that, let me move this down and I'm going to set up our problem here. All right. So once again, we go ahead and do our equilibrium expression or law of mass action. K is equal to, and in our equation, there was, oops, did I move it up too far so we couldn't see it? All right, let's see it, be able to see it. There is, let's see, calcium ions, and they're a product. Hydroxide ions are also a product, and hydroxide ions have a 2 in front of them, so we're going to square it. Okay, and once again, notice that the reactant, the one reactant, is a solid, so we don't include it into our law of mass action. So that's it. The equilibrium expression is K is equal to calcium ions times hydroxide ions squared. And now we can go ahead and go, all right, let's take our calcium ions here and plug that into where it belongs here. And our hydroxide ions here, plug it into where it belongs right there. So we end up with X times 2X quantity squared. That's going to equal to your equilibrium constant, which we said was 5.02 times 10 to the minus 6. Try not to have to scroll up. I don't think it's the end of the world if we did. We can double check. 5.02 times 10 to the minus 6. Yeah, that's where it's at. So notice how, whoops, didn't know I could move that. Notice that's what ends up coming down here. All right, so now that we've got that set up, we can solve for X and find out what the solubility is, because basically X is our solubility. All right, so we got X and we got a 2X quantity squared. 2X quantity squared is actually 4X squared. So we're going to end up with X times 4X squared, right? 2 squared is 4, X times X squared is X squared. That's going to equal to 5.02 times 10 to the negative 6. I'm not going to rewrite that because what I'm going to do is I'm going to collect these guys. And so X times 4X squared is 4X cubed. 4X cubed is equal to 5.02 times 10 to the negative 6. See, it wasn't such a simple like X squared is the other one, but still it's not too bad. All right. Now all you have to do is get X cubed by itself, which means divide both sides by 4. And you end up with, and I'll do all the math at one point, all at one time. So let me move this up here. Okay, so dividing both sides by 4 means that we're going to cancel the 4's on this side. You end up with X cubed equals to 5.02 times 10 to the minus 6. Ooh. All right, let me fix that. All right, divided by 4. Now to get X by itself, what you got to do is now take a cube root. Whatever the exponent is, take that root. If it's to the 5th power, then you take the 5th root and calculate it. You'll be able to find a calculator that does that. And so now your X is going to be equal to 5.02 times 10 minus 6 divided by 4, then take the cube root of the whole thing. So let's go ahead and do that on our calculator here. All right, actually, I think I can go ahead and do cube root of, let's see, parentheses, there we go. 5.02 times 10 to the negative 6. All right, and I can go ahead and divide that by 4. Divided by 4. All right. And I close the parentheses. And that's going to give me 0.0108. Right here, 0.0108. If I round to 3 decimal place, 3 significant figures. So 0.0108. 0.0108 molar. All right. So that's much more soluble than the other one. Not very soluble. You're going to get a little more than 0.01 moles per every liter, but still, it's much more soluble, right? So that's going to be our solubility of our calcium hydroxide. Okay, so that's how you do those problems. Okay, hope that this was helpful. There's other videos that show other examples of how to do these problems pretty much in the same way.